Let me start with something uncomfortable, but important. Most of what people think they know about black holes is wrong, not because they're foolish, but because the subject itself resists simple storytelling. When people hear the words black hole, they imagine a cosmic monster. Something like a vacuum cleaner in space, endlessly sucking stars, planets, and unlucky astronauts into an infinite abyss. That image is dramatic, but it's not physics. It's a metaphor that went out of control. A black hole is not a hole punched into the universe. It's not an empty region where matter disappears. In fact, it's the opposite. A black hole is an object, an extremely dense object with mass, gravity, and very ordinary origins, at least by astronomical standards. Most black holes form when a massive star runs out of fuel and collapses under its own weight. Nothing mystical there. Gravity simply wins. Here's a useful thought experiment. Imagine our sun suddenly being replaced, not by an explosion, not by a collapse, but instantly replaced by a black hole with exactly the same mass. What would happen to Earth? Nothing dramatic. The Earth would continue orbiting exactly as it does now. Same distance, same speed, same year length, no sudden pulling inward, no destruction. That alone should already tell you something important. A black hole's gravity at a distance behaves just like the gravity of any other object with the same mass. So if black holes don't violently suck everything in, what makes them special? Only one thing. There exists a region around them where gravity becomes so strong that escape is impossible. Not difficult. Not unlikely. Impossible. Once something crosses that boundary, no amount of speed, energy, or clever engineering can bring it back out. Even light, which normally escapes everything, fails here. This is why they're called black holes. Not because they're holes, but because they emit no light from within that region. Already, you can see the problem. Our everyday intuition is built on experiences with pushes, pulls, surfaces, and directions. Black holes don't play by those rules. They don't grab you with invisible hands. They don't pull you down in any ordinary sense. They reshape the very idea of what paths through the universe are allowed. And that's why explaining black holes is so hard. We keep trying to describe them as aggressive objects doing violent things, when in reality they are quiet consequences of gravity taken seriously. They are what happens when mass bends space and time so extremely that the usual idea of going somewhere else simply stops making sense. The real challenge isn't that black holes are exotic. The challenge is that they expose how misleading our mental pictures are. They force us to abandon comfortable ideas like absolute space, universal time, and simple cause and effect. Before we even get close to the center of a black hole, our language starts to fail. And that failure is not a weakness of physics, it's a clue. To understand black holes properly, we have to let go of one of the most deeply ingrained ideas we carry from everyday life, the idea that gravity is a force, something that reaches out and pulls objects together like a rope or a magnet. This picture is useful for throwing balls and building bridges, but at the deepest level, it's misleading. If we keep thinking this way, black holes will never make sense. Einstein showed us that gravity is not really a force at all. It is the geometry of space and time. Matter doesn't tug on other matter across empty space. Instead, mass tells space and time how to curve. And that curvature tells objects how to move. Objects fall not because they are pulled, but because they are following the straightest possible paths in a curved universe. A simple analogy helps, even though all analogies eventually fail. Imagine a stretched rubber sheet. Place a heavy bowling ball in the center and the sheet bends. Now, roll a marble nearby. The marble curves inward, not because the bowling ball grabs it, but because the surface itself is no longer flat. The marble is simply following the shape of the sheet. In this picture, gravity is not an interaction between objects. It's a property of the surface they move on. A black hole is what happens when this curvature becomes extreme. Space and time are bent so sharply that every possible straight path leads inward. It's not that something inside the black hole reaches out and pulls you. It's that the universe has been shaped in such a way that all directions point toward the same destination. Asking how strong the pull is misses the point entirely. There is no pull in the usual sense, only geometry. This is also why black holes don't behave like cosmic vacuum cleaners. Far away from a black hole, space is only slightly curved, just as it is around any star or planet. Objects move normally, orbits remain stable. Nothing dramatic happens until you get very close. The danger is not distance, it's geometry. Our difficulty in understanding this comes from how our brains evolved. We evolved in a world where space feels flat and time feels separate. We throw objects, watch them fall, and describe what we see in terms of forces and pushes. Curved space and flexible time are not part of our instincts. They are mathematical ideas that only reveal themselves when mass becomes enormous and distances become cosmic. Black holes force us to confront this mismatch between intuition and reality. They are not mysterious because they break the laws of physics. They are mysterious because they obey them too well. They push those laws into a regime where our everyday concepts collapse. When gravity is no longer a force but a reshaping of reality itself, words like fall, pull, and down lose their meaning. Once you accept that gravity is geometry, black holes stop being monsters and start becoming inevitabilities. They are not violent acts of nature. They are calm, precise consequences of space and time responding to mass exactly as the equations say they must. There is a particular boundary around a black hole that marks the real point of no return, and it is not a physical surface you could touch or crash into. Nothing special happens there locally. No alarm goes off. No wall appears. Yet, crossing this boundary changes the structure of your future completely. This boundary is what physicists call the event horizon, and understanding it requires giving up the idea that space and time behave the same way everywhere. The event horizon is defined in a very precise but unintuitive way. It is the distance from the black hole where the speed required to escape equals the speed of light. Outside this region, escape is difficult but possible. Inside it, escape is not merely unlikely, it is forbidden by the structure of space and time itself. Since nothing can travel faster than light, nothing inside that boundary can ever send information back out. What makes this so strange is that the event horizon is not something you would feel while falling. If you were drifting toward a sufficiently large black hole, you could cross the horizon without noticing anything unusual at all. Your body would not be crushed at that moment. Your instruments would continue to work. From your point of view, physics would seem perfectly normal, at least for a while. But from the perspective of someone watching from far away, a completely different story unfolds. As you approach the horizon, your motion appears to slow down. Your clock seems to tick more and more slowly. The light you emit becomes stretched to longer wavelengths, shifting toward red and eventually fading away. To the distant observer, you never quite cross the horizon. You simply hover there, frozen in time, gradually disappearing. This is not an illusion or a trick of the light. Both descriptions are correct, and neither is privileged. Time itself is behaving differently depending on where you are. The event horizon is not just a spatial boundary, it is a temporal one. It separates regions of spacetime that disagree on what now even means. This creates a deep conceptual tension. Did you fall in, or did you not? Physics answers without embarrassment. Both descriptions are valid within their own frames of reference. There is no single, universal timeline that everyone agrees on. Black holes make this impossible to ignore. The difficulty here is not mathematical. The equations are clear. The difficulty is psychological. We are used to thinking that events either happen or they do not, that there is one objective sequence of moments shared by the entire universe. The event horizon quietly destroys that assumption. It shows us that time is not a universal background ticking away identically for all observers. It is a local phenomenon shaped by motion and gravity. The event horizon matters because it marks the point where prediction breaks down in a new way. Once something crosses it, the rest of the universe can no longer know what happens to it. Information stops flowing outward. The black hole does not announce what it contains. It simply keeps its secrets. And that silence is not a failure of observation. It is a fundamental feature of how space-time is arranged. To really understand what happens inside a black hole, you have to abandon the idea that space is the main thing being distorted. The deeper truth is that time is what breaks first. Space follows later. This is where black holes stop being strange objects and start becoming strange experiences. In everyday life, time feels fixed and unavoidable, while space feels flexible. You can choose where to go, but you cannot choose when. Tomorrow arrives whether you want it to or not. That structure is so familiar that we mistake it for a law of nature. Near a black hole, that structure begins to unravel. Outside the event horizon, space and time behave roughly the way we expect, though already warped. But once the horizon is crossed, their roles change in a subtle but profound way. The direction toward the center of the black hole becomes like the direction toward the future. It is no longer something you can avoid by moving differently in space. Moving inward is no longer motion in the ordinary sense. It is progression. Inside the horizon, asking whether you can stop falling inward is like asking whether you can stop next week from arriving. The question no longer fits the situation. The geometry of space-time has changed so that the center lies in your future in the same way that tomorrow lies in your future right now. No force pushes you there. Nothing accelerates you toward it. You arrive because space-time itself has arranged events in that order. This is deeply unsettling because it destroys the comforting idea that physics is always about forces acting on objects. Inside a black hole, there is no meaningful sense in which gravity is pulling you toward the center. The concept of toward has changed. The center is not a place you move to, it is a moment you approach. This also explains why escape is impossible, even in principle. You cannot escape your own future. Just as you cannot turn around and walk into yesterday, you cannot redirect your path away from the center once you are inside the horizon. All possible trajectories, no matter how energetic or clever, lead the same way because they all lie forward in time. Our minds resist this because we are wired to think of time as a passive backdrop. We picture it as a universal clock ticking away identically everywhere, indifferent to what happens in space. Black holes show us that this picture is wrong. Time is dynamic. It bends, stretches, and rearranges itself in response to mass just as space does. This is why black holes are not just astronomical curiosities. They are laboratories for understanding what time really is. They force us to confront the possibility that time is not fundamental in the way we imagined, but a feature of a deeper structure we do not yet fully grasp. When physicists say that black holes break our intuition, this is what they mean. They don't just challenge our ideas about space and gravity. They challenge the very distinction between past, present, and future. And once that distinction becomes unstable, reality itself begins to feel less solid than we thought. If you follow the equations of general relativity all the way inward, they point to something called a singularity. The word itself sounds dramatic, but what it really means is disappointingly simple. The mathematics stops working. Quantities like density and curvature shoot toward infinity, not because infinity is a physical thing hiding inside the black hole, but because the theory has been pushed beyond the domain where it can be trusted. At the center of a black hole, general relativity predicts that all the mass is compressed into a region of zero volume. Space becomes infinitely curved. Time, as described by the equations, comes to an end. These statements are precise within the math, but they should immediately raise suspicion. Whenever a physical theory produces infinities, history tells us that the theory is incomplete, not that nature has gone mad. We have seen this before. Classical physics predicted that atoms should collapse. They did not. Classical electrodynamics predicted infinite energy and radiation. It was wrong. Each time infinity appeared, it signaled the need for a deeper framework. The singularity at the center of a black hole is almost certainly another such signal. The real problem is that two of our best theories collide here. General relativity describes gravity and large scale structure beautifully, but it ignores quantum effects. Quantum mechanics governs the microscopic world with extraordinary accuracy, but it does not include gravity in a satisfactory way. Near the center of a black hole, both theories are required simultaneously. Neither is prepared for the encounter. As a result, we do not actually know what exists at the center of a black hole. There may be no point of infinite density at all. There could be a new form of matter, a quantum phase of spacetime, or something so unfamiliar that our current language cannot describe it. The singularity may not be a thing in nature, but a signpost telling us where our understanding ends. What makes this especially uncomfortable is that the singularity is not hidden in some remote corner of the universe. According to the equations, it lies in the future of anything that crosses the event horizon. It is not optional. If the classical picture were correct, every infalling object would encounter it. And yet we have no physical description of what that encounter would mean. This forces an unusual kind of humility. Physics is often celebrated for its predictive power, but here prediction fails completely. We cannot say what happens to matter, to time, or even to the concept of existence itself at the center. The equations fall silent, and no experiment can currently replace them. The singularity teaches us an important lesson. The universe is not required to be understandable in the ways we prefer. Our theories are maps, not the territory. When the map runs out of detail, it does not mean the land disappears. It means we have reached the edge of what we know. And black holes mark that edge with brutal clarity. At this point, it becomes important to separate what physics genuinely knows from what it merely speculates about. Black holes are often presented as complete mysteries, but that is not quite true. They are only mysterious in very specific ways. In other ways, they are among the best understood objects in the universe. We know that black holes exist because we see their effects. We observe stars orbiting invisible massive objects at the centers of galaxies. We detect gravitational waves from black hole mergers. We even have images of the glowing material surrounding them. These observations are not indirect guesses. They are precise measurements that match the predictions of general relativity with remarkable accuracy. We also know how black holes formed. When a sufficiently massive star exhausts its nuclear fuel, it can no longer resist its own gravity. The core collapses, and if the mass is large enough, no known force can stop that collapse. The result is a black hole. This process is violent, but the object that remains is surprisingly simple. A black hole is fully described by just a few numbers: its mass, its spin, and its electric charge. Beyond that simplicity, uncertainty begins. One of the deepest unresolved questions concerns information. In physics, information is not an abstract idea, it is a measurable quantity tied to the state of a system. If you throw an object into a black hole, all the detailed information about its structure seems to vanish from the outside universe. According to quantum mechanics, that should not happen. Information should be preserved. General relativity, taken at face value, seems to disagree. This tension leads to the famous black hole information problem. Does the information truly disappear? Or is it somehow encoded in subtle correlations at the event horizon or in the radiation black holes emit? We do not yet know. Different theoretical approaches offer different answers, and none has been confirmed by experiment. We also know that black holes are not entirely black. Quantum theory predicts that they emit a faint form of radiation, now called Hawking radiation. Over unimaginably long times, this radiation causes black holes to lose mass and eventually evaporate. The mathematics behind this effect is solid, but its full implications are still debated. Does the radiation carry information out? If so, how? The difficulty in answering these questions is not due to a lack of effort or intelligence. It comes from the fact that black holes sit at the intersection of two successful but incompatible theories. Our tools work beautifully in isolation, but they resist being combined. We are trying to describe a quantum universe using classical geometry, and the mismatch shows. Human intuition struggles here because it evolved to navigate a narrow slice of reality. We are comfortable with objects, surfaces, and forces. We are not comfortable with horizons, entanglement, and spacetime itself behaving like a dynamic medium. Black holes demand a new kind of thinking, one that accepts uncertainty not as a failure, but as a guide toward deeper understanding. What we know is enough to be confident that black holes obey the laws of nature. What we do not know is enough to remind us that those laws are not yet complete. Black holes are often treated as exotic curiosities, extreme objects that exist only at the far edges of the universe and have little to do with everyday reality. That view misses their real importance. Black holes matter not because they are rare or dramatic, but because they expose the deepest weaknesses in our understanding of how reality works. Every physical theory has a domain where it performs well and a domain where it begins to strain. Black holes push our theories to those breaking points. They combine enormous mass, extreme curvature of spacetime, and quantum effects in a single system. When we try to describe all of this at once, our best ideas stop agreeing with each other. That disagreement is not a problem to be avoided. It is a signal pointing toward new physics. Black holes force us to reconsider what we mean by space. Near a black hole, space is not a passive stage where events unfold. It becomes an active participant, stretching, twisting, and reshaping itself in response to mass and energy. Distances lose their simple meaning. Directions that once felt independent merge into a single unavoidable path. Space is no longer a container, it is part of the drama. They also force us to reconsider time. The idea that there is a single universal clock ticking away everywhere in the cosmos quietly fails. Near a black hole, different observers experience time so differently that there is no global agreement on what events are simultaneous. Cause and effect still operate locally, but the global story fragments. Reality becomes observer dependent in a way that cannot be ignored. Perhaps most unsettling is what black holes suggest about information. In ordinary experience, information feels permanent. Events leave traces. Causes produce effects that ripple outward. Black holes threaten this picture by hiding regions of spacetime from the rest of the universe. Whether information is truly destroyed or merely disguised remains an open question. But the challenge itself has reshaped modern physics. Entire theories have been built in response to this problem. Black holes also remind us that reality is not designed to match human expectations. We often assume that with enough effort, nature will reveal itself in familiar terms. Black holes resist that assumption. They require mathematics, abstraction, and a willingness to abandon comforting mental images. They show us that understanding does not always come with visualization, and that explanation does not always feel intuitive. In this way, black holes act as mirrors. They reflect not just the structure of the universe, but the limits of the human mind. They show us where our concepts break, where language becomes strained, and where imagination runs out. This is not a reason for despair. It is a reason for humility. By studying black holes, we are not merely learning about collapsed stars. We are probing the foundations of reality itself. We are asking what space is made of, what time really means, and whether the universe keeps a perfect record of its own history. Black holes do not answer these questions. They make them unavoidable.